Greetings. Let us continue with the numericals on redundant trusses. Today we'll deal with the numerical number 13, which has a statement: analyze the truss shown in figure. Take modulus of elasticity of member as a constant. Cross-sectional area of the members are given in parentheses, that too in centimeter square. So given frame is an open-ended frame which has roller support at joint A, B, C, whereas joint D is a common joint which is going to connect member CD, member BD and member AD. Cross-sectional area of member AD is 8, whereas cross-sectional area of member BD is given as 6, and cross-sectional area of member CD is 2. At joint D, there is a vertically moving down load, applied load 40 kilo of magnitude 40 kilonewton. If we see the inclination of member CD with reference to horizontal member BD is 45 degree upwards, whereas if we see towards the part of inclination of member AD with reference to horizontal member BD, it is 30 degree. So this frame has to be analyzed in such a way that we should get all unknown forces here, unknown member forces here. So first we have to verify whether this is statically admissible case frame or not. For that we'll find out degree of static indeterminacy for the given frame. So degree of static indeterminacy can be divided into two component parts: degree of external indeterminacy and degree of internal indeterminacy. If we work on external indeterminacy, it's a balance between the unknown forces and available equilibrium equation. In this present case, we have three reactive forces due to roller support at A, B, C, and we have three equilibrium equation available with us. So 3 minus 3 result into 0 means it's externally stable. When we talk about the internal compatibility, we have the equation here m minus 2j, where m is equals to number of members count is 3 here, minus only one joint is available. We can say minus 2 into 1 resulting into 1 value 1, which shows that it is been internally not compatible with reference to the statically admissible case. Hence we can say degree of static indeterminacy equals to 0 plus 1 resulting into a value of 1, means one member forces in excess. So to make it statically admissible, what we have to do, we have to remove one of the member from the given frame. Let us consider we have removed the member CD to make it a statically admissible case, and after making it statically admissible, what we will do, we'll apply a redundant force at the joint C and D in such a manner that it represent the member force as it was in the case of existence of that member in the same line of direction. Once we've got the statically admissible case here, we will find out the forces which has been developed in statically admissible state in other members. We call that as a P analysis. For that, let us prepare a free body diagram for the joint D. If we prepare free body diagram for joint D, we have three forces acting at that joint. Let's say P1 is the force in member AB and P2 is the force in member BD. I have considered here P1 as a compressive in nature, so that the vertical component of this P1, that is P1 sine of theta, is going to counterbalance the externally applied load 40 kilonewton which is going downward. And to counterbalance the effect of horizontal component of this P1, I am considering the P2 be running in a tensile nature, whereas the angle between P1 and P2 is given to us, it's 30 degree. If I apply a static equilibrium equation for this free body diagram from the relation summation of forces in vertical direction equals to 0, we get P1 sine of 30 which is going upward minus 40 kilonewton going downwards. We can say P1 force is about 80 kilonewton in compressive nature. If I apply the static equilibrium equation for the horizontal direction, we can get a relation P1 cos of 30 minus P2 is going towards left hand side equals to 0, hence P2 comes to be 69.28 kilonewton tensile in nature. Once we know the P forces in the member, let's move towards the determination of K forces, that is the coefficient of redundant force. So we'll use here unit load method. So what I will do, I will apply unit load on the line of action of member force CD, so in such a way that it's going to represent the actual effect of the member force in CD. So I will apply 1 kilonewton at both the joint C and D, and I am applying here a unit load in tensile direction. It's an assumption, one may go with a compressive nature also. So after doing so, we will prepare free body diagram for the joint D. Free body diagram at joint D shows that there are three forces acting on the joint D. Very first one is the applied unit load in tensile nature. To counterbalance this, I am going to consider there is a K1 force in a compressive direction, so that the vertical component of K1 will balance the vertical component generated due to the tensile for unit load. And to have compensate towards the K1 force, I am going to consider K2 in a compressive nature, and likewise vice versa the cases will be there. If I apply static equilibrium equations to this free body diagram, we get summation of forces in y direction yielding into a relation minus k1 sine of 30 going downward plus 1 sine of 45 degree. So read this as a plus. By typographical mistake it will appear as a negative here, so please read it as a positive. It's going upward 1 sine of 45 degree, which result into value of k1 as 1.414 kilonewton tensile in nature. Similarly, if we write static equilibrium equation along horizontal direction, we can get the equilibrium of the forces like minus k1 cos of 30 degree going towards left hand side minus 1 cos of 45 degree going towards left hand side plus k2 going towards the right hand side equals to 0. From this, k2 results to be 1.31 kilonewton compressive in nature. Once we know the p forces, we know the k forces, then we'll apply here Cauchy-Gilano second theorem to find out the redundant force in x, which we have considered the force in member CD. So we'll prepare the tabular format to get the here the determination of that force. The very first table will first column of the table will be member AB, BC, CD. We have three members. P forces, we have find out P force AD as a compressive in nature, that's a positive 80. BC as a tensile in nature minus 69.28, and we have taken CD as a 0, means effect of CD we have neglected, we have removed it from the analysis. Now in K1 force we have minus 1.414 because here AD has carried a tensile nature, and whereas BC is in compressive nature of magnitude 1.391, and we have applied a unit load which was in tensile nature, that's why minus 1. Length of the members we can find from the geometric relation. Horizontal member BD was given to us. If I want to find out the inclined length of member AD, the relation I can use here, hypotenuse versus the horizontal, means x by r is equals to cos of 30. From that we get the length as 2309 mm. Similar way we can find out the length of member CD by the relation cos of 45 degree is equals to x by r. X we know, and from this we can get the hypotenuse here, which comes to be 2828 mm. The areas of the members were assigned to us. Areas of member AD was given to us 8 centimeter square, which we convert into mm square as a 800, 6 centimeter square for the BC 600, and for CD it was 2 centimeter square converted to 200 mm square. Now we require the product PKL by A. Since E is constant, I am not going to substitute the value of E here. Now it comes to minus 326.46, means the product of the first of the column 2, 3 and 4 divided by the column number 5th. So it comes to be minus 326.49 minus 445.93, and since CD is 0, the product will be 0 here, and we require summative value of this one, cumulative value of this product. That's why I will take total as the addition of the column here PKL upon A, which results into minus 772.42. The third relation which we require is the K square L divided by A. What we will do, we will take a squaring of the K1 force, multiply it by length L and divide it by area. It results into 5.77 for the member AD. For member BC it's 12.43, and for member CD it is 14.14. The summation comes to be 32.34. We know the relation X redundant force is equals to minus summation of Pi Ki Li divided by Ki square Li. Actually it should be A by E. Since I am going to take the product here PKL A, E is constant here, so E get cancelled in numerator side, and denominator side is going to appear, that's why it get cancelled. For the answer we'll get minus 772.42 divided by 32.34, resulting into a value 23.86 kilonewton tensile in nature. Okay, now final forces. If I want to find out the final forces in the member, force in member AD will be P1 plus K1 times of X. P1 we know the value is 80 and K1 is the coefficient of distribution of these redundant forces, which work out to be minus 1.414 multiplied by redundant force, which we have find 23.86. The value comes to 46.26 kilonewton in compression. Whereas if you go to as a member BD, P2 plus K2X, which comes to minus 69.28 plus 1.391 multiplied by 23.86, resulting into value as 46.26 kilonewton tensile in nature, where we have find of FCD as a redundant force which has a value equals to 23.86 kilonewton. With this we have completed the numerical. We'll be joining further with more numericals related to the analysis of redundant trusses. Till then, stay at home, be safe, be healthy. Thank you.